In this lesson, we're going to analyze some of the core concepts in rotational systems using this question here. So we're going to have a look at the angular acceleration, stuff like the number of revolutions, work done, and power. So you will definitely come across these principles in your studies of mechanical engineering. And as a start, we have here that we have a system with a torque of 6 Newton meters, and it caused some wheel to increase its velocity. Now, typically, you get this with some sort of flywheel questions, that sort of thing. And the velocity that we have here, it increases from 300 RPM to 500 RPM, and it does that in 15 seconds. Now, let's have a look at how we will need to find the angular acceleration. Now, the first thing that we really need to do is to understand the difference between angular frequency and angular speed. And in acceleration, when we're finding acceleration, it has to do with the rate of change in speed. So what we actually need here is the angular speed. So what we're going to do here, we're going to convert these RPM into angular speed. And how we do that, let's take our 300 RPM as the initial, and we're going to take the 500 RPM as the final, because that's the speed that we moved from 300 RPM and then to. So 300 RPM our initial and 500 RPM our final. So what we have to do with this 300 RPM then is convert to angular speed. So we have omega 1, so that's the initial speed now, as 300. And if we just simply multiply this by 2 pi and divide by 60, then this will give us our angular speed. So what we have here is 31.42, and our unit here is going to be radians per second. And we're going to do the same thing to W2 now, which is our 500 RPM. So that's the final angular speed here. So 500 times 2 pi and divided by 60. And that gives us 52.36 radians per second. Now, it's very important for you to understand why we're dividing by 60 in the first place. And that's simply because we're moving from revolutions per minute into radians per second. And if what we had was, let's say this was revolutions per hour instead of per minute, then we would be converting from hours to second. So that means instead of dividing by 60 right here and right here, that means we would be dividing by 3,600. And the same is true if we had revolutions per second, then we just simply needed to just divide by 1 or just multiply by 2 pi. So now that we have our conversion into angular speed, let's see how we find the acceleration now. So our angular acceleration, so that's alpha, equals rate of change, speed divided by time. So what we have here now is just to subtract our final and our initial. So we have 52.36 and we're subtracting 31.42. Now the time all of that happened in, if we take a look here, was 15 seconds. So we need to just divide that by 15. And that will give us our angular acceleration now, which is 1.40, and that's going to be radians per second squared. So that's our angular acceleration there. So now that we have our angular acceleration, let's have a look at how we would then need to calculate the number of revolutions or the number of turns made in that specific amount of time. So for the number of revolutions made in that time, we're going to have to find the total displacement now. So that's the how far has the wheel turned in that amount of time. And we have two options here really. We can use our typical Suvat formula. So theta equals W1 times by our time and plus half the angular acceleration that we just found times by time squared. Or we have another option. We can just use our theta equals to W2 plus W1 multiplied by time, and we do all of that divided by 2 because it's really the average speed that we're working out here, or the average displacement rather. So since we have calculated our acceleration previously, let's go ahead and use this one. But by all means, you can try and use the second formula that you see there, see if you get the same answer. So what we have here then is theta equals our W1 that we worked out previously, and W1 was 31.42. The amount of time is 15 seconds. Don't need to convert that because we actually need it in seconds. And plus now half our acceleration that we just found, which was 1.4, and multiply again by our 15 squared. Now ensure that you square the 15 first before you do the multiplication. Just apply BIDMAS. And what this will give us now is our complete displacement, which on our calculator is 628.80. And this is in radians, so rads. Now that tells us the displacement, but it doesn't tell us the number of turns. And to get the number of turns now, so n for number of turns, what we need to do here is just divide our displacement by 2 pi, which represents 1 complete revolution. And what we end up with here is just our 628.80, and divide that by 2 pi, and we will have 100.08, and that's revs per second. So that's our revolutions there. So now that we have our number of revolutions, we know what our displacement is. The work done and the power is even more straightforward, so let's get into that bit. So to find our work done, we have a few formulas, but the most suitable one in this case is if we use our torque multiplied by our displacement. And our torque is already given to us. Our torque is 6 Newton meters, and our displacement that we just worked out was 628.80. And that's all we really need to do here in order to find our work done. And this is going to give us 3,768.48 joules. So that's our work done. Now power is quite straightforward here. So power is the rate of work done. So work done divided by time really. So then for power, it would just be our work done, but we need to divide that by time. So our work done is what we have here. So 3768.48, and divide that by the time taken, which was 15 seconds. We have a power of 251 and 0.23 watts. So that's our power.